In section 8.5, we're going to learn how to integrate by using something called partial fraction decomposition. Now we know that if we need to combine two fractions, we have to get a common denominator, right? So this guy gets multiplied by the x plus 3, this guy gets multiplied by x minus 4. Don't just forget to distribute your minus sign, and you end up with this. But what if this was the thing that you had to integrate? The derivative of the bottom, you can't come up with that. You can't multiply by an x or anything like that. So we have to come up with a new process. So if the bottom is factorable, then I can take this fraction and separate it into two separate fractions. Now, if you look at integrating this minus this, it's two simple logarithm integrals. So before you get started, there's a few things that you need to check. The first thing, very important, the degree of the numerator must be less than the denominator. In other words, the power has to be bigger on the bottom. If they are the same degree or you have a higher power in the top, then you must use long division first. Once you do that, you're going to end up with a remainder, and on that remainder, you can possibly do partial fraction decomposition. The second thing you have to check, your denominator must be factorable. Okay, for distinct factors in the denominator, so you factor your denominator, you don't have anything that's raised to a power, they're all distinct, then all of your numerators must be 1 degree lower than the denominator. So if you have an x in the bottom, the numerator is a constant. If you have x squared in the denominator and it's a factor that you can't factor farther, then x squared in the bottom means that you would have to have 1 power lower. So if my denominator was x squared plus 4, not factorable, my numerator would have to have x to the 1, but also a constant. Okay, so this is about as difficult as it's going to get as far as I doubt seriously you'll have any power higher that's not somehow factorable in any of these problems. If you have linear factors, say like x minus 3, then you just have a constant. Now notice that your unknowns are not the x's now, they're the coefficients. You have to take something like this and get a common denominator and then set your numerators equal. And you'll see what I mean in a minute. Now, if you have repeated factors or blob to the power, you must have that factor represented in your decomposition to every power starting with 1 and going up to the power that you see in the original denominator. In other words, if you have x cubed, then you have to have a fraction with an x, a fraction with an x squared, and a fraction with an x cubed. Now your numerators, you must have it every power from 1 to the highest power in the original, and the numerators will be based on the base factor. This says x cubed, but the base was just x, right? So all of these numerators for the x's are going to be 1 power lower than x. So they're just constants. And you see that last factor, x plus 1, 1 power lower, and I get that. Now the process, once you decompose your denominators, you have to get a common denominator on the right-hand side, and then you'll equate the numerators. And then you're solving for the unknowns that are now coefficients. Okay, partial fraction decomposition takes a difficult rational integrand and makes it multiple smaller, neater fractions that you can now actually integrate. So what if we had this? We can factor this to be x minus 4 times x plus 1. So I'm going to separate those two factors. I'm going to have one fraction that has x minus 4 and the other that has x plus 1. Both of those factors are linear, or x to the first power, which means that I'm going to have constants in the numerator. Okay, once I get a common denominator on the right-hand side, my equation is in the numerator. So a gets multiplied by this, b gets multiplied by that, and now I have this equation. Okay, process. This equation has to be true for every single value of x. So I can take any number I want and plug it in. If I plug in an x minus 4, this will be a 0. Now, I can't plug in x minus 4 equals 4 up here, but this is the equation I'm solving. So when I plug that in, this is a 5. I've solved for a already because this guy went away. So now I want to plug in x equals negative 1. This piece goes to 0, and you get 1 equals negative 5 times b. And I've solved for b. Now, don't take a shortcut and not write this right here, because when I replace my integrand with my new fractions, it's better that I can see what the a was over. So positive 1/5 is over x minus 4. Negative 1/5 will be over x plus 1. And now these are two simple integrals. The bottom is u, du is dx, so I end up with 1/5 ln of x minus 4 minus 1/5 ln of x plus 1. I can factor out the 1/5 and I can combine the ln's. The positive one will be the top and the negative one will be the bottom. So I get the ln of x minus 4 over x plus 1 plus c, and done. Okay, in this problem, we have to pay attention to how we factor things, right? In this case, I can pull out a common factor. So I'm going to split this fraction up into two fractions, one with an x, one with an x plus 3. Both of those are linear, so I'm going to have just constants in my numerator. Get a common denominator on the right, and write down the equation that's in the numerators. Now I'm going to plug in x equals 0, which gets rid of this guy, makes that 3a, and makes this 1. Remember, you got to plug the 0 in for all of the x's. And I have solved for a. Now I want to plug in x equals negative 3 to get this guy to go away. Negative 3 plus 1 is going to be negative 2 equals negative 3 times b. And I've solved for b. Notice that your numerators are not always the same number like it was last time. Negative divided by a negative is a positive. So now the a, the 1/3, is over x. That's a simple integral. It's just an ln of x. The 2/3 goes over x plus 3. The denominator is u. du is dx. I end up with a 2/3 times the ln of the bottom. So 1/3 ln of x plus 2/3 ln of x plus 3 plus c. And I can factor out a 1/3, make that 2, a square, and both of those ln's are positive, so I have multiplication. Now, if you were evaluating, this would be much easier to evaluate, and it's just nicer to look at. Next problem. Notice in this problem that I've already factored for you, we have a repeated root of x. We also have a quadratic root that doesn't factor. So my denominators are going to have to be the x, then the x squared, And then this is going to have a numerator that has an x and a constant. So here are my denominators, and then I'll go back and put the numerators. This is linear, so I have a constant. This is a linear factor to a new power. We're always going by the base factor, which is just x. This guy, though, can't be factored. My numerator has to be one power lower, all the way down to a constant. Now, when I get a common denominator on the right, this guy gets multiplied by another x and an x squared plus 4. The b already has the x squared, so he gets multiplied by x squared plus 4. And the cx plus d gets multiplied by an x squared. So I'm going to split the cx and the d. They're both over the same denominator. So cx times x squared gives me cx cubed. D times x squared gives me an x squared. So now I can plug in x equals 0, and that would get rid of these two guys and this guy and leave me with just 4b. 0 here minus 4 gives me minus 1 gives me negative 1 equals 4b. I've solved for b, and I'm going to use that. But now I'm stuck because there are no zeros of x squared plus 4. So I have the choice of plugging in more numbers for the x's and getting a whole bunch of equations. But the way I want to do it is by equating the coefficients of the same powers. If this statement is true for all values of x, then I have to have the same number of x cubes on both sides, same number of x squareds on both sides, same x's, and same constants. Now, plugging in x to equal 0, I'm already equating constants. So let's look at the coefficients of x cubed on both sides. I have 0 on this side. This ax times x squared means I have an a. Notice that I did not put the x cubed. My equation is just in the coefficients. So I have an a and a c. If I look at my x squareds, there's none on the left. Ax times 4 doesn't give me a square. B times x squared is here, and a d. So I have these two equations. I've already solved for b. So I can plug in the minus 1/4 right here and get what d is. D is positive 1/4. Now let's look at the coefficients of x. I have 2 on the left. I have 4a here. Nothing here, nothing here, nothing here. Look at that. I've solved for a already. A equals 1/2. Now I can take this and plug it right here, and I've solved for c. C equals minus 1/2. And now I have all of my coefficients. Let's not lose them. C is minus 1/2, A is plus 1/2, D is 1/4, B is minus 1/4. When I plug all that stuff in to all of these, then I'll have my new integrand. This one will be a logarithm because A is a constant. This one will be x to the minus 2, which is just a power rule. Then I'm going to split the cx and the d into separate fractions. So my c is minus 1/2, so I'm going to get minus 1/2 x, which, okay, we'll put it together and then we'll pull it apart. So when I group the x part, that's just a logarithm because the derivative of the bottom has an x, and I have the x here. When I group the plus 1/4 over this, we're going to have to think of something else. So I've got minus 1/2 integral of x over the denominator, and you see if the bottom is u, the du will be 2x. So I can integrate that as a substitution integral. And the last one is 1/4 integral of plain old dx over x squared plus 4. All right, this is 1/2 logarithm of x. or the ln of the square root of x if you prefer. This is a power rule. 1/4 out front, add 1 to the power, divide by the power. We'll clean that up in a minute. This piece right here, we already talked about it. The bottom is u. He's not raised to a power, so it looks like a logarithm. du is 2x dx. I have the x and the dx. I'm missing just a 2. So I can multiply by a 2 and divide by a 2. And that's going to give me a 1/4 ln of 2x. I'm sorry, x squared plus 4. I'm going to write the 2 in the top and the 2 in the bottom. All right, last little bit. I should recognize at this point that this is an arctangent. A is 2, u is x, dx is the du. So I'm going to get 1 over a arctan of u over a, which is x over 2. Plus c. Now we can clean this up a bit. This x goes to the denominator, minus a negative, that goes away. And I can put this and this together, my logarithms. I just have to get a common denominator. So I'm going to multiply this guy by 2 over 2, and that makes him 1/4. And the positive ln is the top, and the negative ln is the bottom. And I chose the 2 from the numerator to be an exponent on my x. This cleans up to be just plus 1 over 4x, and I have 1/4 times 1/2 is 1/8. And that's as nice and neat as I can make it for you. One of the best things that you guys can do to learn how all of this stuff works, this is so big and ugly. Take the derivative of this, clean it up, and you'll see that you get this simple function back as your derivative. All right, in this problem, we have to know how to factor the sum of cubes. Well, this is x cubed and 2 cubes, so we get x in the same sign, 2, opposite sign, always plus. Make sure you know how to factor the sum and difference of cubes. This factor is quadratic. So because there's an x squared, and it never factors, almost never. So this is linear, I have just the constant. This needs an x and a constant in it. Anytime you have a quadratic factor, you have to have both the x and the constant. Common denominator, a gets multiplied by this guy. I'm going to split the bx and the c into 2 pieces to make it easier to solve. So bx times x plus 2 and plus c times x plus 2. All right, now if x equaled -2, we would lose both of these guys. So if x is -2, 6 still equals 6. This is going to be a +4 and a +4 and a +4, which is going to give me 12a. Everything else is a 0, so I have solved for a. A equals 1/2. And this integral will be a simple logarithm. This one we're going to have to mess with. What if x equals 0? That means the b goes away, and this is 4a plus 2c, but 4 is 1/2. So this guy right here is just a 2. Subtract 2 from both sides gives me a 4. That means c equals 2. One more. We can keep plugging in values of x if you want. Let's try x equals 1 because it's easy. So 1 minus 2 plus 4, 6 still equals 6, right? So this guy right here is a times 1 minus 2 plus 4. plus b times 1 times 3, that'll be 3b, plus 3c. So I get 3a, 3b, and 3c, but a is 1/2, and c is a 2, so that makes this a 6. Kind of nice, because I can subtract 6 from both sides. And then I'll have negative 3/2 equals 3b. Divide away the 3, and I get b equals minus 1/2. Okay, this problem is going to be kind of nasty. So let's mark what we found, and then we'll continue. So I don't have much room here. Let's get it written down. A is 1/2 over x plus 2. That's a simple logarithm. Now I'm going to split the bx and the c. So I have minus 1/2 times x Okay, let's don't split it up. Let's see what happens. Minus 1/2 plus 2 over that quadratic factor that doesn't factor itself. And this guy right here is going to be nasty. We're going to have to split it up, and we're going to have to do a lot of manipulation to be able to do this integral. So we're going to continue this on the next page. All right, I'm going to factor a half out of the whole thing. I can factor a half from here. Factoring a half from here is going to make that negative. But if I pull the minus, that becomes a negative, and I factored out a half, which makes it a 4. Just a little bit nicer to look at, that's all. Now, this is simple. This guy right here, if I set the denominator equal to u, then du will be 2x minus 2. I've got 1x minus 4, so we're going to have to talk about some stuff here. So this guy was easy. The derivative of the bottom is the top. I'm going to set this equal to u. Du is 2x minus 2 dx. That's not what I have, but I do have an x. So I'm going to factor a 2 out of there, and I get x minus 1. So I'm going to manipulate my numerator in a special way here. Distributing this 1/2 to this integral. On the top, I'm going to have x minus 1 plus 1, and then the minus 4. Notice that I did not change the value. I subtracted and added the same thing. But now I can group these together and then just have minus 3 over the denominator. So I'm going to split this into two fractions, two separate integrals. So copy, copy, copy. I'm going to keep the 1/2. I'm going to split this into two separate integrals. I've got x minus 1 over the denominator. That's a 1. See, that miraculously changed to a 1 over the denominator. Now this guy right here is a minus 3. So I'm going to split it into two integrals. I've got a minus 3 and a minus half gives me plus 3/2 over just dx times that denominator. Well, that's going to be difficult to integrate, so we're going to have to think of something. All right, over here in my little cheater box, I've got my denominator, but if I take half of the 2 and square it, it's a 1. So I add a 1, subtract a 1, that gives me a perfect square, x minus 1, and this is a plus 3. So I'm going to write it that way, and you'll see that this guy is a logarithm, This guy is an arctan. Where this is a squared and this is u squared, and du will be dx. So copy this. This is minus 1/2 ln. Oh, wait a second. I needed a 2 and a 2. That gave me 1/4 on the outside. Now, when I write my final answer, I'll get a common denominator and combine. Now this guy right here, 1 over a is 1 over root 3. I already had the 3/2. Now you see that the 3 and the root can cancel, and I actually end up with the square root of 3 over 2, because 3 over root 3 is just root 3. Arctan of u over a. Plus c. And now, like I said, I'm going to multiply this by 2 over 2, get a common denominator, which is 4, and that's going to give me 2 ln of this, which is the ln of that thing squared. And I've got 1/4 ln. That's a positive one, so x plus 2 squared over the other guy, x squared minus 2x plus 4, plus we had 3 over root 3, and that canceled. Arctan. Remember, arctan has 1 over a in front of it, of u over a, plus c. Nice.